Hey everybody, welcome back to this WeeW episode where we are going to set up the ADC peripheral for the STM32F1 going from scratch, and also have a display on the using the UART communication to see the result for both ADC1 and ADC2. So you can see here the circuit that we do have. We do have two potentiometer, each one respectively connected to a certain ADC in the microcontroller. And when I change, this is the ADC2, so this is, I'm going for the ADC2 to 0. So you can see it goes to 0, and here the ADC1, which is like in the middle, and put it a full and then put it to the 0. So if you'd like to learn how to make it and how this is working, just follow us in this new episode. Before jumping to the video, let me take the moment and thank everyone for their support. I will keep doing my best to provide this quality content. So as usual, to support the channel, you can give us a thumbs up, make a comment, or subscribe and stay tuned. So as usual, the code that we are going to use is available on GitHub. You can find the link in the description below. We are going to use a C language, and the program to code will be Kale version 5. Finally, the level here is WeeW, but if you follow up it will be quite simple, so keep up with us. So for the hardware, so we are going to use the blue pill, which is the STM32F1 based microcontroller, and after that we are going to also need the FTDI or the FT232RL to establish the UART communication with the computer to display the result. Finally, we are going to use a variable resistance or a potentiometer to have a check of the change of the ADC. So for today in the tutorial, we are going first to have like a review for the STM32F1 ADC, and then we are going to jump immediately to code, where we are going first to set up the ADC init, and after that, having the check for the ADC, we will get further details about this function, and after that we are going to take a look and get the result from ADC Read, and finally ending up with an example and having a debug if needed. Okay, so let's have a detail about the STM32F1 ADC. So first of all, let's have a look on what is an ADC, or analog to digital converter, which can be said as an ADC or A/D or A to D. So which is a system that converts an analog signal such as a sound picked up by a microphone or light entering a digital camera into a digital signal. This is Wikipedia. So in other words, you take the real world signal, whatever temperature, humidity, whatever happening within this world, and then you go it through the ADC, which is converted to a certain electrical signal, and this signal goes to the computer, that number that can understand. So that's as simple as it is. So this is an ADC. So let's go be more specific now and take a look to the STM32F1 ADC. So first of all, it's a 0 to a 3.3 volt. So be careful if you are using some component that requires 5 volt working voltage. And then this is a 12-bit ADC, which is really fantastic. So you do have value from 0 to 4095, or you do have 4096 values, which is already very good for such a small and cheap microcontroller. Then it has 18 multiplexer channel, 16 from external, 2 from internal. In other words, do not complicate it, you do have 16 pins that can be used as an ADC sensor, but not simultaneously. There's some ways to manage it, but just be careful, you can't set up all the pins at the same time to be an ADC. And finally, so you can have up to 3 ADC for the STM32F1 families, but in the case of the blue pill, you will have only 2 ADC. Okay, so now that we had a review about how this analog to digital converter works, we can jump and start setting up in the blue pill. So this is our main program. So here we do have quite an empty one, and I added the ADC library, which is 2 empty libraries for the moment. So the ADC, the header, I'm adding the GP drive library, and this is GPIO drive library, and also the system time library, as we will need for a certain and a very short time to have a small break. And here where we are going to write our code to initialize the function. So this is our main program, and we are going to start for the initialization. So first of all, before we jump to coding directly, let's understand what we are going to do. So the first thing is to jump to the datasheet and to take a look on which bus we are going to work. So let's go as usual to this very simple map to understand where is our bus, and here we are. So the ADCs are in APB2. Okay, so if we would like to initialize them, we just have to go to APB2, look for the ADC 1 and 2, and just activate it or set the bit to 1. Then, so if we would like to know which pins can be an ADC, we just go here to the pin mapping, and here you are. So you can see the ADC 1 to channel 0 is pin A0, and so on until we find the last channel. I just summarized everything here so you don't find it by magic. So from PA0 to PC5, the total number of the pins that we would like to initialize. So these are the pins that we can make as ADC, and we can start from here to our function to set it up. So first of all, we need to make sure that that pin is the pin that is used to initialize the ADC is the right pin to use. So first of all, what we need to do is to confirm. So let's have two variables where we call them both char, and the first one is a channel, and this one we will define later on because we have 16 channel, and so the channel here, and after that we have the char also for the result, and we put it initially equal to 0. Okay, so it's a little bit wordy, but we have to go through this one. If port is equal to the PA, so as an input for our function, so first we are going to define if it's ADC 1 or 2, so we do have 2 ADC, and if the port, which port are we going to select, and the pin within that port. So if it's equal to PA, okay, so let's go here and start. So if this is equal to PA, if the pin that we are going to select is less than 8, as you can see here, the PA7 is the last one. So if it's less than 8, then we can say that result is equal to 1, so we can move on. And also the channel is equal just to pin. Very simple, quite easy to move with this one. So else, if the port is equal to PB, port is equal to PB. So here also I need to add this one here. So the result is equal to 1, but the channel is not equal to pin, it's equal to 8. So as a PB we do have 8 and 9, so it's not only equal to PP, and we still need another condition actually inside it. If the pin, let's put here, pin is less, actually it's just one condition, pin less than 2. Okay, so then we can add this one here. So the channel is equal to 1, 8 plus pin. So this is how the result will be. And finally, so this is else if, so another one, we can actually use the same just to gain time, and this one is equal to PC, and if the pin is less than 6, okay, then the result is equal to 1, so it's quite a positive result. And so the channel is equal, so we have to take the first one, the equal 10 plus the pin. Okay, that's perfect. So that's the number of channel, and here we do have the check if we are inputting the right pin for the analog signal. And why I'm putting this char here is to return if there's a misinput. We can easily have a return which is 0 and negative, or a false return, so we can be sure that something went wrong. So here then what we can do, so if we do have a result, okay, we can start doing some code. So first thing that we can do, and very simple, is use the JP library. So we do have the init JP, so this is to initialize the pin, and we're adding here the port, here the pin, and after that whatever the pin, we would like to have it as an input and as an input for an analog signal. Okay, so this is the first thing to do. Then we can go and be specific about which ADC. So let's start first with if ADC is equal, and just to show you here, I put it ADC1, define ADC1 as ADC1 and ADC2 as ADC2, just for purpose. So ADC1. Then let's see what we have to do. So let's jump to the reference material. And first of all, we need to jump and activate within the register of the clock. So go to clock register, and as we said, we have to go to ABP to enable. So we have to enable the alternative function, and also we have to enable the ADC1, okay, which is the bit number 9. So what we have to do is just to go RCC and APP2 enable, and we put or equal, and as we said, it's the pin number 9, so 201, because we are also enabling the alternative function. Okay, so that's the first thing, and after that we can jump to the ADC specific register. So let's go to the ADC specific register. Quite very simple and easy for this ADC. So we jump here and we go to the registers. So first of all, we have to set up to 0 this register, because there's so many setup here. We would like to put here to 0, so we are sure that the CR2 or the control register here, there's no any extra setup. So what we can do is RCC, no, not RCC, actually ADC 1 and CR2, it's just equal to 0. We clean everything from here, and after that we have to review which channel we would like to scan or to review. So this is quite a very important step and very simple one. So this is here, if I go, let me open it again. So which bit I would like to use to control my register. So if I go to this one, 3 here, so we need to put the number, the channel, to this one here. So in the ADC regular sequence register, we just have to put this one. So just to give you an idea, I will have a full review about how to use more pins at the same time, but this is a little bit more complicated. But if you are going to use only one bit, you have to set up here the bit that you would like to use. So you have to go to the ADC SQR3 and just set up here the channel that you would like to add. So let's go here and we go, so ADC 1 SQR3 and equal to channel. Okay, so here we are saying which channel I would like to scan, and after that, like, we almost finished here. So we have the channel, we have to power on the ADC, and it's quite very simple. We go back again, so let's go back again to this one, and it's CR2, so control register 2 here, and you just have to put add-on, or let's go here quickly, So yeah, the AD converter on off. So but here where there's a very tricky one. So you have to put once, put it 1, but after that, to power up, you have to put 1 again, or set up this bit again. So be careful, if you put it only once, the ADC will not be working. You have to put it twice with a small delay function. So that's why we are going to use delay function. So ADC 1 and CR1, no, actually it's CR2, and or equal 1. We are putting a large delay just because it's starting, like here, 100 millisecond, and then put this one again to officially start the converting operation. Finally, I would like to set up this function to provide a continuous reading. So what we are going to do is to go to CR2 again. Let me open this one, and I would like to have a continuous conversion. What does mean a continuous conversion? Means when we finish the conversion, we keep doing again and again. So this is not ending. So we go here and we put ADC1, and this one will be equal to 2. And that's all. That's what we need to prepare our ADC converter 1. So now that we have this, let's put again else, and we add if here like this, if it's equal to ADC2. So this one we are needing to put the pin number 10, so the bit number 10, so this one become 4, and all the rest here is just ADC2, 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 and ADC2. That's all. So this is how we initialize, and last step, at the end of everything, we have to return result. Okay, let's save. Oh, not 0 but result. Add a new line here, copy this function and add it to the header. Okay, should be fine. So if I copy this function here, I already added my ADC drive library. So if I put here ADC1 and port, I will say PA and pin 0. Let's put this one, and it's 0, not 0N. So let's save, build. Okay, so we do have 2 warnings. Something is ending without end lines. And let's go back again, save, build, 0 error, 0 warning. The program is compiling, and this step is good. So we have completed the initialization of the analog digital controller. Now we are going to have this function to set up the ADC check, which is the step before reading. We have to be sure that the microcontroller had enough time to read the data and put it in the data register. So we are back again on our ADC drive, the C file, and we are going to start creating this function that will check if the data on my controller is ready. And this one is used as same as the previous one, so it returns a 0 or 1, which is a true or false, and it has, first we check about which ADC, which port and which pin. So let's go here and start. So as usual, a very simple one. So we have char, let's call it a check, and this is the one that we are going to return at the end, so we put it as equal to 0. Okay, and here let's put return check. So that will be our final result. So to check that, so let's go quickly to this reference manual, and this will be in the status register, and we need to check if, like if we go here, this one, not this one, will be end of conversion. this is the one that we need to check. So when the conversion is ended, we just check on this one, and if it's equal to 1 means complete. So that's very simple, and just by reading it, it will become 0. So let's go back here, and as usual, so we have to put if ADC equal to ADC1, so we can really copy exactly the same thing from here and paste it here, delete what is inside because we don't need it for the moment, and also inside this one we need to check the condition. So let's go and check this one. So we have to say if, and inside this one, so we have to put actually double one, it's the opposite. So if ADC, this one, so actually we don't need that one. So what we can do, if, let me remove this parenthesis, put here, so ADC1 SR, and let me find the end, and 2. So if it's happening, if N2 we have 1, so then we can put check is equal to 1, and that's all. That's what we need. And exactly same for this one. So let's copy. So if the ADC2 is equal to 1, then check is equal to 1. And this is what we need to do here. We need to confirm if this is the conversion has complete, and if the conversion has completed, we can start reading it from the file. So that's all for this part. It's quite simple but very important. So now let's copy it and add it here. Probably I will need to add no, like the space is good. So let's put this one inside the main loop. So actually this one shouldn't be here but should be here. We don't need to run it all the time, we just have to put it only once. But inside the while loop, this is what we need to do. So for this one, as we set up the ADC1, we are going to check the ADC1 and the PA0. Okay, and what we can do, just use if here. We don't need to put this one, and check it. Okay, so here we do have the function ready to be used. So let's again save and build to check. There's 0 error, 0 warning, so we are ready to jump to the final step of the code. So we got our function ready, so for checking that we are ready or not. So now we can be able to start building the ADC read function. So this is the function where we do have a reading from 0 to 4096, but we are going to modify a little bit to have an output between 0 and 1000 to have a more better idea about the proportion of the change. So here we are at the last part of the code. So before going to testing, so this is the function that we are going to build. So this is like it will return an integer as it is a 12-bit result. So we can put it as a short, but I prefer integer just in case. And we are going to get some result, and as usual what we have to input is the ADC. Are we going to use ADC 1 or 2? Then the short, so which is the port that we are going to get, and the pin. So let's put here the function that we are going to use. So we will need to have a result, so we'll put it as a result here. This is what we are going to return, and we put it as a 0. And let's go here and put return result. Okay, so after that, so let's put some data. So as I told you, I would like to change the result, not something to 4096, but it will be something based on something related to 1000. So let's have int data, and this one will be used later on, and that will be equal to 0 for the moment. So quite very simple, straightforward. As usual, we can copy this one, even this one is too much. So if ADC is equal to ADC1, then what we are going to read quickly to show you guys, but you already I guess you already know where to get this one, the data register. If I go here, this one, you just read the data register here, and it's only 12-bit that you are going to read. Okay, so let's go here. So it will be ADC1 DR. No, actually it's the opposite. So we are putting it, we're going to put it data equal to ADC1 DR. That's all. And else, let's put here else, let's go here and add this one. If it's equal to 2, data will be ADC to like DR. Finally, result will be equal. So first of all, I'm taking the data multiplied by 1000 and divide by 0xFFF, which is the full length of the reading that we do have, and we return the result. That's simple as it is. So now we can read the data from our ADC converter, and let's add this one here. Let's check if we do not have any line, and let's start using this one in our main program here, and we are going to put, as I said, ADC1 port A and pin 0. Okay, this will provide us quite a reading of the data. So now we do have our ADC converter working perfectly. So next step is to have an example. Yeah, congratulations! Now you have a functional ADC on the STM32F1, and we are ready to start an example and maybe debug if we have an issue. So now we are going to use the UART communication with the PC to visualize the data and to visualize what the input is coming, plus the multimeter to read what is the voltage and compare. So also I'm going to add the potentiometer to make a variability and check if things are same or not. Okay, let's go for the last step. Okay, so this is our last step, and let's first of all initialize our UART function. So let's include here the UART, so include and UART drive. Okay, .h. If you would like to know further, and this is the first time you're reading from this one, there's a whole video explaining how the UART function is working. So what I'm going to use here is UART init, and we are going to use UART2, and the baud rate will be for 115,200. Okay, and also I added the help function because we need to convert the number we are getting from here to something that we can send through the UART. So let's get some data set up for the UART. So first of all, we need to have a number here, so kind of a small string, so a char, an array of char that we call number, and that will be around one, like let's put 10 and see if things will go well or not. Okay, so that's perfect, and we need also another number, an int, that we will call analog read read, and that will be equal to 0. Okay, so let's put this analog read here equal to our ADC function. Okay, and I think here we are good. So if we read this one, so what we need to do after that, we need to convert this analog read to the array. So we are going to use this help function to change this one, and we convert, we can do it int to char, and we put the integer, which is the analog RX, and the chart that we would like to read is the one input inside is this one. And after that, what we can do is just sending this string. So what we can do is just UART send, and it's UART2, and we would like to send number. After that, we are going just to add a new line using the UARTX 2 and just 1, and like this. Okay, so this one is, oh sorry, I always have this confusion on this one. Okay, that should be good. Let's run. 0 error, 0 warning. So let me show you now the project that we put it in place. So this is a multimeter here, and this is here our STM32F1. I connected actually 2 pins because I wanted to check if the ADC2 is working, and there is a P0 and P1. Each one of them is connected to a potentiometer. So first of all, I would like to have the reading and then compare what we are going to read against the multimeter. Okay, so let's put this one here. So let's save, build, and load. Okay, things looks fine for the moment. As usual, I'm going to use the H term to read the data for the moment. And okay, so there's nothing coming. So let's start debug then and check what's going on. This one is working. Okay, I know why this is not working. It's quite very simple and straightforward. I have to put the init for the sysdig. So if I add here sysdig init, it's quite a very big mistake. And let's go back again. Yeah, we do have a data here, and this is 274 like thousand compared, like it's the quarter of the value of 3.3 volt. So like if we would like to convert it further, like let's bring in this one here again and make some complicated stuff. I don't want to go to floats because floats make the microcontroller extremely slow. So what I will do is to convert this one a little bit. So analog equal, so I can just multiply by 330 and put again analog equal, let's put analog again but divided by 100. Okay, that should give us something almost near. So if I save, build, and put here, so it gives me this number of volt that I do have. So let's go now, open the camera and check with the multimeter if we do have the same stuff going on. So let's try to zoom. Now that's not fair. Okay, so the multimeter is ready and I'm going to read. So let's take this one, and just for the sake, you see here it's 900 and stable. So let me just a moment confirm which one is a 0. This is the 0 here, and if I decrease to 0, it's almost 0 here, and if I start increasing, the maximum here is 3200, so which is 3.2 volts. So let's try to read here, and if I put this one and this one, I should start. Nope. Yeah, so you can see that it's exactly the same, but let's put in the middle on this one, and it's almost there. Don't forget, when adding a multimeter, I'm adding some kind of variation. So here we have 2.2 where here is 2.1, but if I remove, something will change a little bit. That's quite weird. It should increase a little bit. let me put it again. Okay, so here we do have 2.2 and here is a 2.1, so there is a small gap, and this is not only coming from the microcontroller but too many multiplication added in the way. So I will show you later on in next videos how to play with this one, not inside the microcontroller. But you can see we are not that far from each other. There is a small mistake, so if I remove this one, it's not that big gap, but we can read the analog data. Now, just for the sake of confirmation, let's add also the use of ADC2 just in case. So let's add here ADC2, and we are going to read PA1 as I already connected. And what we can do is, so I know where is the mistake now. So also I need to make empty string empty, and I have to put for this num, else some trouble will happen soon. Okay, let's save, build. Okay, that should improve the situation, because previously, okay, so now changing a little bit. Okay, it's not moving on. Okay, so what I have done is quite yeah, like I should have put both, or just it's quite this one should be ADC2. Okay, so that was a mistake. And what I have to do now, so I will move this one to the end. Let's move this one to the end and add here, just to make this one, let's, sorry guys, so I'm enjoying this one a lot. So we have to read everything again, copy all the stuff here, and ADC2 PA1, and here same stuff happening, but what we can add between both just in case. So let's have UART send, so where we are going to send an array, and putting here a small sentence like this, just to put, or let's put ADC2 like this, and this one we can put here ADC1. That will make a little bit of more comprehension. So let's save, build, and load, check what's going on, so you can see the difference. So let's put the camera on. So this is the ADC2. So now I'm increasing the ADC2. You can see here the ADC2 is increasing, and this is the ADC1 that I will put to 0. So ADC1, as you can see, is a 0, ADC2 is like a full. So you can see that we can read from two ADC at the same time. Okay, so I hope you enjoyed this tutorial about the ADC. There is more coming about how we can read from many channels in one shot, and also for the interrupt. Thank you so much again, and see you soon. WeeW!